Estou te explicando que eu não.
Hello. Well, my name is Alberto Ortigo, and I'm going to present this seminar, which is going to we are going to talk about embankment on soft soils and lessons learned, especially from mistakes. Uh, I'm a geotechnical engineer. I have to to introduce myself. I'm a geotechnical engineer with lots of experience. Now it's about 55 years. I've been working on geotechnics. I happen to be a fellow of the International Institution of Civil Engineers in London, and a chart engineer as well, and a PE in America. Okay, and welcome to my seminar. I hope you're going to enjoy, and I'll be always available for discussions. Okay, so the what we're going to talk today is lessons learned after 50 year. Here's a mistake here. Lesson learned after 50-year experience, common problems. Site. We are going to talk about site investigation, how I learned, okay, and ground improvement solutions that have not worked, and we're going to try to understand why. We're going to talk about instrumentation monitoring of embankment soft soils. And in the end, we are going to talk about the philosophy of how to deal with soft soils. And this is the most important part of the presentation. So let's start with problems, okay? This is a few things I've seen during my career, failures, big failures like this, and this took place in a remote site, which I saw this hydraulic rig sinking into the soft clay due to lack of bearing capacity, a bearing capacity failure. And later on, north of South America, I've seen this happening. It was a stitching machine which was installing weak drains in the soft mud. In this case, also due to bearing capacity failure. As a matter of fact, I had a few days before, I was talking to the contractor, and I told him that I was very skeptical about the bearing capacity of this soft clay. And there was a small 30 centimeter, 40 centimeter layer of sand, and I want to put a geosynthetic in the contact between the sand mat and the soft soil. They didn't do, and that's what happened. And also, I've seen many failures on soft clay. This is an embankment. This embankment was only 3 meters high and failed. Uh, Also, this took place was a very deep failure in a very high embankment with lots of cracks. So these things can happen, and they do happen if you don't do a good work, a design work. Also, I've seen too many settlements on approach embankments, and this is a kind of reinforced earth with concrete uh, wall, and these elements were totally displaced. The settlements here were about 30 centimeters, and we saw the disalignment of this. And then I did a design review after the failure and recommended ground improvement, etc., etc. So I've seen lots of things like that. And also, these are one of the, I was very young at this time, that was built in 1978. I visited the site at the time. I was young. I was not involved in the soft clay. We had here 18 meters of soft clay. It was the government printing office, and the buildings were piled. So, as a matter of fact, I visited the site to carry out pilot tests, static pilot tests, which I did, and they didn't have any solution for the rest, the surroundings of the buildings. So later on, I visited the site in 2006. they asked me to carry out a rehabilitation design to improve the problems they had of settlements all around the buildings, etc. And I did that in 2006, so a long time ago. So let's start talking about site investigation. And of course, we have many methods to carry out site investigation, like the SPT, the CPT, the dilatometer, the pressure meter, and the VST, vent testing. And we're going to address some of them, not all, because lack of time. And as a matter of fact, I have published in the past. I was a professor for 25 years, and during that time, I published a couple of books, and I'll be able to to send them over to you. The first one is about some mechanics, the light of critical states theories, and the second one was about slope stabilization in mainly residual soils, and I'll be able to send them over for anyone who sent me an email. My email is going to be at the end of the presentation. And if you send me an email, I can return you with these books and other publications I have published in the past. So we have two types, two characteristics of soil of in situ tests. One is for profiling, in which we have all the data along the depth of the soft clay. And the profiling test, we have the stratigraphy, we have parameters usually obtained through correlations, okay? And we have calibration tests. Which are the calibration tests? The stress and the formations are known. Okay, so we can classify in situ testing these, and in the calibration test parameters are obtained through numerical analysis. Okay, and which are the profiling tests we're going to address today? SPT, which is very common, CPT, of course, with pressure measurement, then we call it CPTU. We are going to address Vinci tests and the Marchetti dilatometer. And these tests allow we get parameters through empirical correlations. And what are the calibration tests? The most important one is the back analysis of trough embankments. And I did this many times in my life. I'm going to show you some examples. And we have the pressure meter, we have the self-boring pressure meter, we have the Menard pressure meter, we have the plate loading test, and we have the horizontal plate loading test. But we are not going to address these pressure meters, self-boring pressure meter, because they are too difficult to use. Also, I use Menard pressure meter a lot, but in hard soils, not soft soils. Okay, and these ones, plate loading test is mainly for pavement design. Horizontal plate loading test I've done in the past. Today I do not do this. I use the pressure meter. But these methods, we can use a rigorous analysis through numerical methods. So this is the aim of the lecture. In terms of variability, SPT uses enormous variability, up to 6%. It depends very much on the energy which is transmitted to the sampler. CPT-M is the mechanical CPT, is the old one. We don't use that anymore. We use the electrical CPT, in which variability of the CPT and the DMT, the dilatometer, they are very small. Usually, if you run several tests very close one to the other, they give almost the same result. So it's very good. Pressure meter also, although I don't use for soft soils, only hard soils, they yield a large scatter. And self-boring pressure meter is very difficult. I've done this in the past 30 years ago. This is very difficult. I don't do that anymore. And this some data from the late Professor Puhawi. Also, the variability of soil properties. Usually, the properties that have the least variability is unit weight, okay? And friction angle as well, phi or tan phi. However, on the other hand, hydronic strength have a very large variability. This is the compression coefficient from the Virgin curve has a very large variability, and this gives you an idea, if you do lots of tests, what kind of variability you may get. And let's talk a little bit about the SPT. SPT was developed probably in America in the 20s or 30s and still used, very much used, still very helpful. And in the past, we use this kind of equipment, which is a donut hammer, and we have a weight. This weight is 75 kilos, is a mass, as a matter of fact, and the drop height with a drop height of 76 centimeters. And we have a standard sampler, and we count the blow count, we count the number of blows to drive or to push the sampler into the soil. And usually we use for the first 15 centimeters, the second 15 centimeters, the last 15 centimeters, 45 centimeters, the maximum the sampler can go into the soil. And then we just take the number relative to 30 centimeters of the sampler. And these very standard. We're going to talk about this later on. So also we use a lot, almost every project we have drilling sampling, and we have a variety of samplers which differ the quality of the sample and the price, etc. Usually when we have very soft clays, we use tube samplers, okay? Film to soft, film to hard, tube sampler, Shelby tube. If we go into very hard soils, usually we use the Denison sampler. The SPT is always necessary, and we have, of course, rock samplers for when we enter rock. The SPT sampler is standardized in many standards, and the diameter of the sampler is 50 millimeters. The internal diameter is 35, but this is a thick wall sampler. What happens that the sample that comes into the sampler is very much disturbed. So it's very good for characterization of the soil, but for obtaining properties from the sample obtained by this method is out of question. It's very much disturbed. And then these are typical SPT borehole log we have carried out. This is a project in Guyana with very soft soil at the top, and the soil after some meters, after 10, 12 meters, start to the SPT number or the N index N from the SPT start to grow, and it goes up to 50 at a great depth. Okay, and with this is the reason it's very difficult to get correlations with SPT for very soft soils. It's almost impossible. Very soft soil will fall in this area, and then if you have a SPT less than 5, it's almost impossible to get any good property or reliable property with this. But if you have SPT of 20, of over 10, it's possible that you can have an idea of what should be, for instance, the Young's modulus at 50% stress level. Okay. On the other hand, if you want to obtain properties, you have to use tube samplers. There are several ways. This is the most common one. It's a Shelby tube with thin wall. Usually the wall is about 3-4 millimeters, and then you push that into the soil, into the soft soil, and you have a valve here. When you push, the water comes out. Okay, and when you push the sample out, this valve is going to close and make some vacuum at the top of the sample in order for you to get a good recovery of this sample. Okay. Uh, these are different diameters of uh, the Shelby tubes I have used in the past, from 50 millimeters to 100. I have used up to 120, but this is not here. And these are 125, yes. These are 125, but this was not a Shelby tube. This was a better sampler, a stationary piston sampler, which I'm going to show you. And then, many years ago, I did a research. It was part of my PhD research long ago, 40 years ago, in which I took samples of different diameters and I trimmed them to different diameters as well. So there's the sample, there's the specimen in different diameters, and I checked the quality. The idea was to check the quality. In the beginning, I thought this was the best sample, the greater diameter, and the specimen 36 millimeters was very good. And then this is this is about CPT. CPT came later. I first saw CPT being carried out in 1975, so a few years after graduation. And in those days, most CPT were mechanical, and electrical CPT, the first one I really, the first attempt I saw was 1976 or 7. I don't remember, more or less about this time. And so let's talk about, a little bit about CPT, which CPT is the main tool for very soft soil. In general, soft soils with SPT, they can give you an idea of the depth of the layer, but you can't analyze any property out of that. And these are two main references which I have used. This is from Peter Robinson. He published Guide to Cone Penetration Test. It's free out of the internet. I recommend you to get a copy of that. And this is another book. It's a book by a friend of mine, Fernando Schneid, from the south of Brazil. And he is a specialist in situ testing and wrote this book, which is very interesting. Okay, in terms of history, the first one to carry out a simple mechanical cone was Barrington, and then many other people start doing that. This Houtje Maschinenfabrik, they invented the Dutch cone, they used the mechanical cone, and after the Second World War, and then lots of developments. But really, until I think these came to the press by after 1975. Until then, not very much. So, and this is the electrical piece of cone, which we use today, in which we measure three parameters: the tip resistance, the pop pressure at this position here, and the friction at this sleeve. So it's an electric instrument with load cells to measure the tip resistance and the friction. And also there's a transducer here to measure pop pressure. And this is very much the main site investigation tool we use today. There are many standards today, and one of the best standards is the STM, very good standard. But if you almost every country in the world has a different standard, but STM is a good one. And this is the first one I've seen. Imagine this was electric cone, and everything. There was no way of digitalization, so everything was plotted in a plot like that. And this was the first one. He was a student, Camilo Borges. He was a student at Federal University of Rio, where I worked, and then he did his MSc on this. It was the first time I've seen one. And later on, we after leaving the university. Well, no, that was before I left the university. We developed, we made piso cones of 50 MPa, which was very good and behaved quite well. Not in the beginning, but we learned with that. Then we had this, all the electronic students that did the data acquisition system for us. Uh, this was, and this guy also wrote the data acquisition software, which was very good. And here we have the inclination because we have a tilt meter inbuilt in the cone. This is the tip resistance, lateral friction, pore pressure. This is what the operator sees on his computer screens. The first, the first time I've seen a CPT was in 1975 by that guy that wrote the thesis on that. And this was the kind of light rig we used. It was a mechanical rig which was used for mechanical CPT, and we adapted it for the electrical CPT as well. And then in 1991, I worked as a visiting professor at the UBC, University of British Columbia, with Professor Campanella, and I learned a lot from him. And this was the truck which we used to go out every week, one day on the field, and 5 days or 4 days analyzing the results. The amount of data that we got from one day in the field was enormous because this was a very good equipment. And we also did lots of, with this hammer, we used to do a lot of seismic CPT, which I'm going to address briefly later on. Okay. And this was 1995, was we made a new cone and we started doing seismic CPT in Rio de Janeiro, in Brazil, and where I taught as a professor. And this was the first thesis that we have done with this equipment. But we did a lot of projects overseas, like this one in Ecuador for a dam. So we just sent the cone, the equipment, and the technician, and we adapted a drilling rig to do the test. Not the best one, but that was possible at the time. So we did lots of tests in this project, very interesting project, and this is the cone being pushed into the ground. We did also in Peru a couple of projects with the also adapting a cone. That was 2007. In Hong Kong, we worked with Fugro this truck, and we did a project at the World Trading Center. No, it's not World Trading Center. It's a World. I forgot the name. Anyway, it was on Hong Kong Island in 1997. I did a project like that, and also this was the best, by far the best truck I've ever seen until now. It was in 2002 in Holland by this company, Moss Grand Mechanica in Holland, and this truck is fitted with tracks like this, so it can move in very soft ground, in poor ground condition. And this inside the truck, it's very interesting. It has two hydraulic chucks. Chucks is the what holds the rod. So one is so the pushing doesn't stop. Okay, the pushing continues with these two holdings, two hydraulic. We used to call them the chuck. Okay, so this is the hydraulics, very modern at the time, serious. And this was the data acquisition. Of course, data acquisition today should be much better. And we also had this, we designed this calibration frame. We had a mechanical engineer design this for us. And we did calibration with our equipment before every project. Before we start a project, we did a calibration and test using this calibration frame. And also, we had to learn how to saturate the porous element And this was tough in the beginning. But then I found this. I remember I went to the dentist. I found this vacuum pump, and I went to a medical supplier to buy something like that. And this is sonic bath. The sonic bath is used to clean the porous elements. So we used a lot this. And saturation was a big problem. It still is. If you don't know how to do that properly, you get very poor result. That's why I'm going to talk a little bit about that. And what you have to do is you put a cone like that. And I learned this with Professor Campanella, the late Professor Campanella. And we put a cone like this, a plastic cone, a plastic funnel, and we put the silicone oil or usually silicone oil, and then we saturate the porous element here, the cavity, with the syringe. And here is Professor Campanella teaching me in 1991 how to do that. Okay, uh, this is the cone, uh, how we do, and this the aired water. Or we usually don't use de-aired water. We use 50% de-aired water with glycerin, and this has to be de-aired first before we go to the field. And this is how to use the syringe to saturate the cavity. And here the cone is ready, and we use a condom to protect against loss of saturation. We put the condom here. And one of the things that Professor Campanella did very well was to find about the problem of unequal end areas. And the reason is it's impossible to have this diameter at the tip equal to this diameter of the rod. And why? Because you have this tip here, the little lateral tip. And so because of that, they found this by doing offshore tests, because they used to calibrate the cone or zero the readings before going into the water. And then when they put the cone into the water before entering the soil, they found out the readings were not zero anymore. And then Professor Campanella studied the problem, did lots of tests, and found also that there were cones in which they have different areas and also unequal in areas, not only at the tip, but at the friction as well. The friction is very simple to solve the problem. It's just you have to machine them with the same, this value has to be equal to this value here. So most cones today, they don't have any problem with the unequal end areas of the friction sleeve, but they have on the tip. And the tip, what you have to do in order to calibrate is you put the cone into you apply water pressure on the cone by having something like that. And the ideal cone would have the water pressure, applied water pressure, the same as QT. Okay, this would be an ideal cone, which is impossible. So all cones, they have a deviation from the ideal situation, and the A value is what we call the area ratio, and the area ratio allows correction. So most cones have this area ratio equal to 0.8, okay? And this is the correct value. Until Professor Campanella, we used the QC. And today we found out it's absolutely necessary to use the correct value, which Professor Campanella called QT. And that's what we use today. And this is about pore pressure measurement quality. If you do a pore saturation, that's what you get. A pore response with long pore pressure values, usually like this, okay? And usually what we have is pore response until a certain level, and then when the pressure increases a lot, you get much better results. This didn't occur in offshore work, because offshore you always have a very high water pressure. Okay, so you don't have this. This is inland application, has been very common. If the saturation was not so bad at certain level, like this case, about 10 meters, then you're going to have quick variation of pore pressure like this, and then you can tell that these pore pressure are correct. These are not. Okay. And if you have a very good saturation, that's the kind of plot that you have. You can see it from the plots. Okay, you can see it from the plots. And this, for instance, could be if you do a dissipation test, which we're going to talk about later, you can have this drop, or could be a sand seam. If I have a sand seam, this could happen. And the other thing which is very difficult to avoid sometimes is cavitation. Cavitation takes place even if the cone is very well saturated, and this looks like to be the case, but at this stage here, it enters a hard soil. And when it enters a hard soil, mainly here, you have this, this here was because there was a dissipation test. But when it enters a hard soil like this, okay, much harder, then you have cavitation. This sometimes is very difficult to avoid. And that's why you have to use pore pressure information with care, okay? And in the past, people leading with offshore, they use pore pressure for classifying the soil. Today, we tend not to use because sometimes we cannot trust the results because of cavitation. This is impossible to do. This is a case where there was a strong the blue line here. There was a strong layer, and this led to cavitation from the start. So by looking at this strong layer at the top, I received the data. I remember this very well. It was a soft clay followed by other materials. And I asked the operator to do another test by pre-drilling here. Okay. He drilled down to 1 meter, 1.5 meters, I don't remember. I think 1 meter. And did it again and see what happened. The pore pressure increased. The pore pressure in the red is much better than the pore pressure in the blue. And here, a slight difference, but it's not very important. Okay. So we repeat the test. Sometimes we have to do that, and that's why we always have to look at the data before the drill rig or the CPT rig leaves the site in order to ask or not to carry out another test for some reason. Okay, and stratigraphy. When I start looking at the CPT data, we only have this. We had sand if this QC was hard. We have clay if QC was low. Sand and clay, that's what happened. And then it was developing with time. And in 1991, that's what I used to do. I used to do my own plots. I used to do by, there were graphs that we could classify the soil. And this was tests carried out in Richmond, Canada in 1991 by the EBC truck, with the EBC truck. And this is stratigraphy that we analyze here. As you see here, very interesting. Here's sand because it's very hard. And then if you look here, it's a soft material. And then you see the pore pressure going up. These are ratio pore pressure increment divided by QC. In those days, we still didn't use QT all the time. So we had a soft layer here. Here we have some sand seams. Okay. Here another clay seam, and then soft clay from Vancouver. And also this we can see here the existence of a clay seam very well. Then these plots were available at the time in 1991, 92, more or less. we had this classification, which were developed by Peter Robson, also Professor Campanella. They publish a lot, and we use this, as I've told you, in the past we used QT, and then we start using the QT, which was corrected, and what we found that these plots with the pore pressure parameter, the pore pressure parameter was calculated U2, the measured pore pressure minus the hydrostatic pore pressure QT minus the total stress. And what we found was that this is not a reliable classification method because we cannot trust sometimes the U2. Then, sometime in 90, I don't remember when it was released, but a few years later, Peter Robson came up with this idea of SPT, solid behavioral type. It was a major development because then we could have these standard colors, which helps us a lot to identify the type of soils we are dealing with. And software became available. Until then, I used Sigma plot. I'm going to show you how I did that. Sigma plot is very similar to an Excel spreadsheet in which we can program, but Sigma plot is easier to make very good plots. So today we have lots of software available, but I tend to use especially this one by Geologsmiki, has been supported by Peter Robson. I also worked in the early stage of this software. I worked with the guy. His name is John Ioannidis from Greece, and he does a very good work. We have developed a few plots like that. Before that, I used either CPT INT from D. Campanella. The software was developed at UBC, and I did my own with Sigma plot. And also for liquefaction analysis, we have this, which I have used in the past, very, very interesting. And so this is how I did the data process in 1991 by using the software I wrote, which of course had lots of limitations. And here we see sand, and then a very homogeneous soft soil without sand seams from the pore pressure. Although we may not use the pore pressure for classification, it's very important to have it. Okay, if there is no cavitation, you can trust, but sometimes we had cavitation. And then later on, I think 20, in the 20s, I don't remember when I started to use the 2005, something like that. These software was developed by Geologsmiki with lots of support from Dr. Peter Robson, and also I helped John to test, etc. But Peter was the main support for this software, which is very good. I still use it a lot. Okay, it has been improved, and this has all these parameter estimation available, so you can estimate the constraint model, the shear models, the undrenched strength, the undrenched ratio, and I would say every 6 months or so, there is a new development, something much better. So this software is very good. Also, deformation models. When I started, I used mainly Sangleha correlations. Now they are outdated. Of course, we have much better. This the book, Sangleha book, the first book I read about the CPT. And today we have much better software, much better correlations, and I trust this one that came later on by Kuhau in Maine, very good. And all these, the best correlations are included in that software. These are proposed by Peter Robson in 2022, and it has been included in CPT. It's very good. We can rely very much on these values of M, and I'll tell you why. So by going from QT2M, which is the constraint models, or sometimes people say Young's models, we can easily calculate settlements by this kind of equation. And in my experience, I have used this for many projects. It's very, very reliable. Today, for instance, I don't use Dometer test to calculate settlement. And why? Because the data set is very, very big, and you may have the results are too much. They have too much scatter, and I do prefer to use the CPT, the cone, and these I can say that this is very, very reliable. The other thing that we do a lot during the penetration in clays is dissipation test. And what's dissipation? You stop the penetration, and the equipment go into dissipation mode, in which it reads the pore pressure change with time, and usually plot against square root of time, seconds, square root of seconds, and here's the pore pressure. So here we have a typical dissipation, here a typical dissipation, here dissipation, here typical dissipation. The yellow one is no dissipation. What does it mean? It's high permeability, should be sand. And also, if we go into an over-consolidated soil, the dissipation can be in the other direction. I mean, the over-consolidation of very hard soil, the delta U is going to be negative. So when we stop, pore pressure goes up to the hydrostatic situation, and that's what happens. Okay, so this is the same soil. This is the same test where I have done this. This is 2022. This is a tailings. And then in this material here was more over consolidated. That's what happened. The dissipation was in the other direction. Why this dissipation in that direction takes place? And this is, you have to look at dilation and contraction. So if you have a sample that dilates during shear, what happens? The particles tend to go apart. If they tend to go apart, what happens to the water between the particles? The water pressure drops. Okay, the contrary effect. So when you have dilation during shear, you always have a decrease in pore pressure. Pore pressure go down. And if you have contraction, if the material is contractive, it's just the opposite. We have the decrease in volume, okay, and the pore pressure goes up. And this is the problem that may lead to liquefaction. If you have contractive material that leads to very high pore pressure, you may have liquefaction. If you compact the soil, if you use compaction, this is what happens. You make it much more stable, because during shear, this compacted soil is going to increase the volume, and pore pressure is going to decrease. So that's why compaction is carried out. Okay, and these failures that took place, killing lots of people, of Brumadinho, of Samarco in Brazil, is because of this phenomenon, which we are going to discuss later on. And CPT designs, it evolved along. I remember the first time I went to the Institution of Civil Engineers in London to attend a conference on CPT. It was 1984, okay? And there was a discussion whether they should use 2 load cells or 1 load cell should be the pore pressure. They didn't know at the time how to analyze or what was the importance of pore pressure measurement. This came later on. In 1904, it was not very much recognized. And then since in 1975 was one of the first projects to do that, and then it evolved And today it's Professor Campanella named the on the cone on the face of the cone E1 position 1, this position 2, and this position 3. So today most standards require that you use 2. You may have 1 or 3 if you like, but 2 is compulsory. You have 2. And today I don't think we need 1 or 3, we just need 2. That's my view. And how to analyze the radio consolidation. There are all these methods, but the one I like most is this one, Hosbin T, Hosbin T, and they are very good for any stiffener parameter. Stiffener parameter is G over Cu, and for non, it's a nonlinear model. It's the piezometer type of cavity, and it's a 2D analysis. That's what I use. It's simple. It's also inbuilt in the CPT program, which I use, and I recommend anyone to use that program as well, which is very good. There are others, of course. And this is the graphical method to obtain T50. This was my contribution to that. I remember I told John how to do that, and I did a lot of tests on that program. So you plot pore pressure dissipation against square root of time, and then the graphical method was developed by at UBC. Lots of people working on that, especially John Sully. And so we used we plot this line, we determined U naught and U100 at some stage, and then you calculate the T50. You take the time for 100, time for 0, calculate here T50, and then you this is the method, we extrapolate the line, obtain U naught, obtain U100, obtain U50, obtain T50, and then we come to this equation, and this was developed by Hosbin T in 1988. This is the radius, this is the stiffness index, which CPT calculates for you. And this for you two positions always, the T50 is always 0.245. And then you enter the time, which you calculate graphically, and it gives you the number, for instance, 336 square meter per year. And however, the problem is there's a lot of data scatter. It's not easy to define which should be the design value. I'll give you an example. We had a lot of scatter here, and then for this depth we had these values, and these in square meter per year, it's about 8 or 10, and then I decided, for instance, to use that design value. And then we have a database which we have putting together for a number of years from many projects in South America, in which we have an idea of what the values could be. And so we always calibrate the value that we get through this database. Let's talk a little bit about vein sheet testing. The first to use the vein was Olson in 1919. Schemto did a lot of work. The first test in Brazil was carried out by my professor at school, Professor Raimundo Costa, in 1949. And also, there was a professor in São Paulo, Milton Vargas, which did the work more or less at the same time. And he was my professor at school, so he told me a lot about this, and I learned from him. And 1950, the SGI equipment, the Swedish equipment was designed, and later on, we based our research on this. And from 1974 to 80, I worked as a research engineer at the Road Research Institute. And also, I was at this more or less the same time, I was giving lectures at the Federal University of Rio. And I worked there from 74 to nearly 81. And I did a lot of interesting research, which I'm going to show you here, some of the results we did with the vein testing. So this is the traditional interpretation. The endurance strength is 0.86 times the torque over pi, and the diameter elevated to 3. But this applies to square, not square, rectangular veins, okay, which should be, in my view, standardized. Roth came out with this later on in 1984. He came up with the proposal change, but in the end, after analyzing all that, he said, no, let's keep the original equation. So we still use the original equation. And this is the VST. How we do that? We install a vein. The vein has four sides, and we rotate it. We measure the maximum torque. I'm going to show some photographs of the vein. And then we give 10 full rotations and do another test, and we take the remolded value as well. So in the research we did, we published in 1985. No, it was later on, 1988. Sorry, it's wrong. We published at the STM Vinci Test Conference, which took place in Tampa, I think 1988. This is wrong. And we proposed a classification. This is the first time which the STM standard still allows us to use to drill a hole, to push the vein, okay, without protection. The B type is which the rods are fully protected. The A type, in which there is a transducer or a way of measuring the torque. Today, this should be used, perhaps. In those days, we didn't have this. And this is the most advanced one at the time, in which the vein was protected by a shoe. And then when we came to the site, we pushed the rod into the soil, and there was no contact with the rod with soil. So there's no friction, okay? And we did, so it capitalized unprotected vein in borehole, unprotected vein in protected rods, unprotected vein in unprotected rods, but we can have a torque cell here, which is very useful, or the protected vein in protected rods. So this is the equipment types that I've seen. And we did a lot of work with this kind of equipment. And what we found, first of all, all these tests were carried out in a soft clay, and they were very close. The boreholes were, say, 2 meters apart, and to a depth of 11 meters, more or less, which was the depth of this clay. And then what we found, a very large scatter of the data scatter, okay? And we tried to use the idea that came with the SCM to analyze rod friction by taking off the vein and using a dumb rod. And what we found is this was nearly impossible, nearly impossible. So the maximum torque that we have from the friction were too high. So no way of doing that. And then we redesigned the equipment. This was part of our research by protecting the rods, and there was no contact, no friction, and also putting bearings to align the rods, okay? And by doing that, we found out we have much better results. The scatter is much lower, and the results were improved a lot, okay? And what we found about the ESCM, we went to this ESCM conference in Tampa. I went, and we presented our result. There was a lot of discussion about that, and there was Skinner, forgot his first name. He was a professor at the Imperial College in London, and he proposed that we had, since this test is semi-empirical, he proposed to standardize the vein, and this was accepted. And unfortunately, this didn't came in the even the SM from 2018 doesn't bring the ideas that were discussed at this conference. Also, they say no load condition friction measurement can be performed by replacing the vanes with a blank stem. Only if the torque. No, no way. We found that this is impossible, and I think this is wrong. And by doing that, by doing lots of tests, we have this kind of soft clay properties. This is the site that the Road Research Institute did all the research. So we had the plasticity index is about 70, the unit weight about 13 to 14 kilograms per cubic meter. The void ratio is 4, reducing to 3 at the bottom, and this is the undisturbed, and this is the remodeled values. The soft clay has a sensitivity of vein sensitivity of about 4 maximum, so it's not very much sensitive. And for this IP of 70, Bieron, which published his ideas in 1972, proposed that we have a correction about 7.7. In the beginning, we carried out 3 or 4 experiments, and we didn't find the need to carry out a correction like this. Okay, this was 1976. I'm going to tell you about the experiments. But today, I don't believe in that finding that I proposed in 1976. That was when the embankment was built. Today, I suggest that most vein results should be corrected with for the sake of safety, with a correction factor of about 0.7. Okay, and also the problem with this is that even if you do a very good result from this or another site, and you do have a lot of scatter, and then to come up with a design profile is something that you have to take care and not use the average, but use something below the average as a design profile. Okay, then we developed a database. This database is from many sites I have worked in the past, and I have also always this undrained strength ratio database, which I can, from a new project, I can analyze and see if the data are reliable or not. The other thing that I learned what to do is I always do a calibration of the CPT. Doing what? By doing a calibration against the vein test. So when I do a site investigation in soft soil, I always propose an island of investigation. What's an island? An island is when you have a CPT, you have a vein, you take samples. So at least 3 boreholes, CPT, vein, and the other one sampling, to do some laboratory tests in order to calibrate the parameters. And by finalizing the site investigation in soft soil, the question is, how much should we invest in a soft soil project if you have a huge project? So this plot shows the total increase in construction percent of tender price versus the site investigation investment. Okay, if we invest 10% of the project price in site investigation, you have very small variation. Of course, this is too much. So this depends. Usually, on the risk of the problem. But you see here, if you invest something around 2%, in most cases, you're going to be, the variation is not to be very high. Ground investigation typically costs 1 to 2% of the substructural cost and 0.5 to of the total building cost. This is this guy what he proposed. Okay, minimum. That's my view. 0.5% for embankment on soft soils. Okay. Now we're going to start ground improvement, but I'm going to propose a 1 minute or 2 minutes break, and then I come back to discuss this. Okay, just 2 minutes, right? Okay, shall we start? Let's talk about ground improvement. And these are the methods that we can use, these for all type of soils, but we are going to concentrate on soft soil. So we're going to talk about vinyl replacement, drains for consolidation, compaction, not compaction piles, not admixture. We're going to talk about deep soil mixing. I'm not going to talk about ground freezing because ground freezing is very affecting sand materials. In clays is not that good, so good. Remove and replace as well. Okay, this is the list of ground improvement that I used in the past. So we may have a light embankment material. I have used that, but this is very expensive. And we have buoyancy effects, limits its use. Remove and replace, its price can vary, but max usually the depth should be 3 meters. Beyond that, the cost is very high. Weak drains with temporary surcharge, mainly in clays. Okay, the cheapest one, but you have to look out for sand seams, and also the temporary surcharge should stay at least 6 months. So we have to allow time. Stone columns is usually requires a drain strength above 10 kPa if unless you encapsulate the stone columns with geosynthetic. Okay, the price can be affordable if you have gravel on site. Okay, and but less more expensive than the weak trains. Jet ground columns and deep soil mix and poly embankment, they are very good when your allowance for settlements is very small. Okay, usually, for instance, I do that in bridge abutments. I tend to use the most expensive solutions. So, but they are about 3, 4 times more expensive than the weak trains. So it varies, depends on the application. If you have time, you use weak trains. You don't have time, you use the other solutions. And how I learned by using, by carrying out shrine banks. This is very important still today for many when you have very large projects. At the moment, for instance, I'm having a big project with a company in Texas in Guyana, and we did a lot of trying backs, a lot of trials there in order to decide which would be the best solution. And in my time, I started the first embankments, try bank I did was 1975, stone columns, 1977, and all these three and all these four were research projects for the Road Research Institute, and this one was also a research project, but it was used by the Jutunaíba Dam designers. I'll talk a little bit about that. Then I have all these projects in between, and I'm going to talk about this, one of the last, and back on deep soil mixing columns at the in the south of Brazil for airport. Okay, so I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 embankments, and that's the way I learned, and I've talked about that. So the first one was the tri-embankment stone column. I was very young, just graduated. I graduated in 1971, so this is 4 years after graduation. And I was invited by the contractor to help them with the instrumentation, because at that time I have designed all the instrumentation for the Road Research Institute, so I had a good experience on the design of instrumentation, and they invited me to help them with that, and I did. So these are the soft clay properties at the site. So we have here, more or less 70% IP. Gamma was about normal values, about 14. And however, the strength was above 20. So a good strength. Usually soft clays are worse than that. Most of them I've seen. And this was about 20. We did this research with that equipment that I've shown you later on. And it was the contract was an Italian company that came to Brazil to carry out this project, but the designer decided to carry out this trial. So the stone columns were installed like this. They installed 520 millimeter casing with a vibrator, and the columns were spaced 2.5 to 3 meters. And this was the early stage of stone column. Then they put poured the gravel, and then they pushed the casing with the vibrator. And this was the construction method. And they carried out 2 trial embankments. And I was the one who installed all the instrumentation in the foundation, and I checked everything. So these 2 embankments were 5 meters high. The soft clay the SPT was null, and they were 65 meters in width, and the soft clay was 50 meters deep. The instrumentation consists of hydraulic piezometers, inclinometers, settlement plates, lots of settlement plates, lots of hydraulic piezometers. We use twin tube hydraulic piezometers, which this was the development I did at the Road Research Institute. And we use also mercury manometers. This was technology which we don't use that anymore. But in those days, there were several dams which used this kind of technology, which I designed. And so we have these two embankments, and this the height of the embankment, the time, and the settlement. So what happens that the settlement with the stone column, which costs a lot of money, was just 20% less. Then the lessons after a long time of discussion by the designer. I was very young. I was not involved in this discussion. These stone columns were not efficient due to small diameter casing, large spacing, which vary from 2.5 to 3 meters. Okay, and why? Because the installation method was not very good as well, and so in those days we didn't know how to design proper stone columns, which now we know. And how. Later on, in the late 70s, 80s, the people from Keller, they developed this Boston feed installation method, in which the stone are compacted as you push the installation tool out. Okay, this vibrates and compacts the stone column. And the stone column also today they have a very large diameter. It's about usually 9 centimeters. It's not like 50 centimeter, which was used in the past. Why bottle feed is better? Because it's fast installation rates, less soil disturbance, much better gravel compaction, better for column continuity. We don't have defects, too much defects, and we avoid this. Okay, so this is what we learned, but fortunately we learned on a trial, and the solution was not used for the harbor. This was a development for the iron ore stockpiles in that harbor, and it was not used. Then in 1975 to 80, and this was the research that I worked as a young engineer for the trial embankments. And we did 3 trial embankments here. This is Rio de Janeiro, this is Guanabara Bay. And then we applied the same technology to Tunaíba Dam, which is 100 kilometers from north of Rio. Okay, so this is the Brazilian Road Research Institute, RRI, in which I worked from 1974 to 81. And it's about 30 kilometers from Rio, so not very far. This is Sarapuí River. And very close to this, I did a lot of site investigation in a big area until we found this area, which had 11 meters deep soft clay. And this was the first embankment which was taken to failure. The second embankment was built in order to test the ground improvement methods which were available at this time, early stages. And then we also did on access roads to build this embankment too. And we used geosynthetics. We used geosynthetics in different ways here. As a matter of fact, I gave this presentation in September in Louisiana at a SAA conference, and I'll be publishing a paper. So I submit the paper to the proceedings of the Institution of Civil Engineers, and hopefully it's going to be published next year, 2026. And this was the failure that took place on the first embankment that I designed on 7 December 1977. And this was the result. We had an embankment, the embankment height by the time of the failure was 2.8, And we did a lot of back analysis at the time, but in those days we did have Windows. Everything was so difficult to use. The computer was mainframe. We had to use Fortran programs. And we found that with mean VST values, the factor of safety that explained the failure was about, with the back analysis, was 0.96. So that the conclusion at the time was if we use the mean factors, the mean VST profile, we can get something like close to 1. And the lesson were the maximum backend height was 2.8 meters. The back analysis with mean and correct VST strength yielded a factor of safety of 0.95. And Bierron's VST correction did not apply. That was defined at the time. Today, I prefer to correct the values with factors with the reduction value of 0.7. VST equipment improved to avoid friction and translation. We found out the VST equipment was very poor, and we decided to redesign, and that gave much better results. And also, we learned a lot about the instrumentation, and was locally made. I designed. I was directly involved in design, except the inclinometer that we buy from Slope Indicator. All the rest was I was involved directly in the design, and this was my PhD thesis long ago, 45 years ago. And then we designed the Embankment 2. The Embankment 2 was designed to check the methods that were available at the time and what were being used as ground improvement. So we used the sand drains, which have been around for a very long time, and we use Frankie type equipment to install the sand drains. And we had two methods because there was a discussion, should we clean the mandrel during installation or not, or the casing, the case of the mandrel. And so we use open mandrel and closed mandrel. The open mandrel we cleaned twice during installation. And then there was another technique which was being used by a company in many roads in South America, the jet sand drain, in which they installed this with a jet, water jet, and then the clay would be cleaned, and then they filled up with sand before extracting it. And weak drains was a very new a very new technique, and this was brought to us by a Japanese company which made this kind of drains. Okay, but they installed the drains unprotected weak drain installation. Today we don't use that anymore. I'm going to address this later. But they have a very light equipment. This was good. A very light equipment on rails to install the drains, but the drains were not protected during installation. This is not good today. And then we use also another section with non-woven geosynthetic with drains. We had no idea whether this would work or not, but this was a proposal, and we used the woven geosynthetic. This was a failure, and I'm going to explain to you later. It's here. What happens that the permeability of the geosynthetic, non-woven geosynthetic in the horizontal direction is high, but there's no way the water would come out nicely. So today we don't use that anymore. I was on site most of the time during this project, and I remember I took these measurements, and so this is the initial installation of the ground improvement technique, the drains, and the embankment height when it started to go up. This was just the initial layer in order to install the drainage system. And what we found is that the closed mandrel produced, these measures were made with hydraulic prism very close to the installation point. And the closed mandrel led to very high pore pressure during installation. The open mandrel much less, the jetted much less, geotextile much less, and weak drains, very small pore pressure. So I have no doubt that the weak drains were the best installation method. And here we have the settlements. We did calibrations. This is the section without the section with no drains, and here are some section with drains. So we found the no drains. That was a settlement. This the equipment the embankment was raised to 2 meters. And later on, much later on, was raised to nearly 4 meters. And what we found, the jetted drains gave the largest settlement. And why? Because it disturbed the soil. Now we have this kind of method was not used anymore because we found it disturbed the soil. The sand drains were more or less no big difference between them. Okay, so the sand drains were not that bad, but the cost is higher. Weak drains are much better, and that's what we use today. These no drains, no woven, but what we do use today is the plastic weak drains, but improve it. And here was not improved, and we have this problem with installation. And so the techniques were techniques that were used in the 70s. Now we have much better, but we have lots of lessons that we learned from this experiment. Jetted drains increases settlement by 40%. Sand drains increase the pore pressure. Non-woven weak drains did not work at all, okay? And composite weak drains yielded the best result. That's what we found. And then we have the access road. The access road was a very interesting project. We had to build that access road in order to be able to build the embankments. And then Rhône Poulain, which was a French company, came to us and, what about if we give you the geosynthetic, you test? Of course, why not? And then we designed an additional experiment in order to test the application of geosynthetic. This was the research carried out by a very young engineer. His name is Enio Palmeira. And Enio today is a professor emeritus at the University of Brasilia, my good friend. And we work together in many projects. And he became twice the president of the IGS, International Geosynthetic Society. He's a world-class specialist on geosynthetic. This was his first work on this. And anyway, this was built in 1979. So this access road was about 1.2 meters high, 4 meters wide, and the geosynthetic, the base. And we have a magnetic sensometer and a hydraulic settlement gauge that Enio and I designed to measure settlements, okay? And we used the no-woven geosynthetic given to us. The weight was mass per square meter was 400 grams per square meter, and the strain at failure was 30%. And this we used in many different ways of applying. This was Professor Palmeira's MSc thesis in 1981, and we did in different ways of applying the geosynthetic. In the beginning, I thought this wouldn't work. And why? Because we had the failure of embankment 1. And the failure of embankment 1 happened when the strains at the base were 5%, more or less. I calculated that. And this strain at failure of this geosynthetic was much larger. And I thought, may not work. Let's see what happened. Lessons. Measured settlements were from 100 to 200 millimeters in different sections. Measured strains were 10%. The bearing failure occurred at the control section without geosynthetic. Reinforcement effects over 200 trucks passed. We measured the amount of trucks. Prevented bearing failure. Reduced settlements by 20%. Reduced embankment volume by 20 to 25%. But how? We didn't know in the beginning. Later on, much later, it was found out that the behavior of geosynthetic when they have confining pressure is totally different. When you have a confining pressure, you decrease the strain at failure a lot. But these were not known at the time. So we learned a very good lesson. In the beginning, I was very skeptical about the whether or not we should go to do that research. But since it was given, let's try. And the results were excellent, very interesting. And then by the 1980, a friend of mine who was a late professor from University of São Paulo, Paulo Cruz, he was a good friend of mine. He was designing this dam, which is about 100 kilometers north of Rio. And this dam was not very high. It was just 12 meters high, but very long. It was this big part, 1 kilometer on soft clays, and here sands as well. The spillway was in the center. And he was very much concerned about this. And he asked me to see him. We went to the meeting, and what about we carried out a trial bank out of the not at the same place. Let's do it 100 meters off the dam site. Oh, let's do it. And I helped him to design. We took the equipment. I asked the permission to the Road Research Institute to do this as a part of the research. And we did a lot of laboratory tests. We did vein testing, and the scatter of the data is very much more than the data scatter we had at the other research site. As you see here, the average is about 20, and we have some peat layers. Okay, and these tests were carried out later on at the Road Research Laboratory. Very interesting data. And then this was the main decision to obtain a design and drainage profile. The scatter was too high. That was the problem. And the consequences were also costly if they use a factor of safety too high. So in order to decide to put the berm or not, and what should be the length of the berm, they decided, Paulo Cruz, the consultant, and the designers decided to carry out a trial embankment, and we helped to do that. And then I invited a friend of mine who came to the research. Now he's a professor in the University of the North of Brazil, Recife. But Professor Continho, now at the time a very young engineer, came to join the research team in order to do this experiment, and this became his PhD thesis later on. So we installed the bank was fully instrumented, and we had lots of inclinometers, piezometers, horizontal extensometer. Also, we have this vertical magnetic extensometer as well. So lots of instruments, and it was a successful experiment. And the lesson we obtained through the experiment, the embankment failed when it was about 80 meters high. So the slip surface could be very well located through instruments. The mobilized mean and drain strength of failure was 20 kPa, okay? So very close to the mean value of the vein sheet testing. And the key information for the dam design, provided key information for the dam design. And so these lessons were very important for the design, and the berm was not too long because they could use these values. Okay. Later on, we had some projects with weak drains and temporary surcharge, which work quite well. And in order to do that properly, we put always Leo geotextile. In general, the strength it's a bidirectional strength of 50 kilonewtons per meter. And then we have a sand blanket. We install the weak drains. Usually the spacing is 1.2 to 1.5 meters, not more than that, we learned. If necessary, we use a geogrid for reinforcement. We put up the embankment, we put the temporary surcharge, and later on, after 6 months, we take it off. And this was a very interesting project that we carried out in the 90s, I don't remember when, in the north. It was the Hansen Lagoon. We did all around the lagoon. It was a big project, 6 kilometers of perimeter, and we used the weak drains. These weak drains were much better because if they kink, they don't stop the water coming out. These were much, as you see here, it's a mixture of plastic that doesn't allow it to kink and to stop the flow. Okay, and was installed by a stitcher with the drain was protected. So much better technology we used in the 90s, and these are the results of settlement measurement at height of embankment. So here we put the surcharge. Then the surcharge were removed sometime, and we see here when we removed the surcharge, practically the settlement stopped. And here the surcharge remains, as you see, the settlement goes on. So we had very, very good results from this. Here, for pressure measurements, I was directly involved in these measurements. So we saw the weak drains here. We see very little change in pore pressure. Here we put the surcharge, and when we put the surcharge, the pore pressure goes up quickly, and we see soon after, 30 days, almost 30 days after the surcharge, the pore pressure decreased a lot, okay? So showing the weak drains were very efficient. And then this was a mistake. They put a stockpile nearby. And when they put that stockpile nearby, this is when the surcharge was increased. And they put a stockpile nearby. I saw it. I thought, no, I have to take this off. And when they took that off, we saw when they put it on, the pore pressure built up very quickly. But by taking it off, the pore pressure came back. And this is a project which I always enjoy seeing the results because it's a nice area, and this is the embankment, and this is the cycle path where people cycles. And I have been coming here for many years, 10 years after we didn't see any settlement evidence. And from this, what are the main lessons about weak drains? We should this I wrote in 1998. I wrote a standard for the Department of Roads, and we came up with these ideas. So the cross section should be limited to 70 centimeters, not to have in order not to disturb very much the soil. The sand mat, minimum 40 centimeters of sand, and we always have to. This is a mistake I have seen this many times. When this area is very large, we may not have drainage. So, in order to ensure drainage, we can either design something like dams, a sandwich with gravel in the middle. At least one possibility, or to use a woven 2D geosynthetic like this with plastic pipe, perforated plastic pipe, in order to drain the water accumulated in the sand net. And also the spacing. Usually I like the spacing from 1.2 maximum to 1.8, but I don't like 1.8. 1.8 is too large. Usually, I like spacing, let's say 1.2 to 1.5. This is my experience today. And why not to have less than 1.2? Because one drain may interfere with the other. Usually, if you put a pile in and a pile close to that, these piles, they must be in soft soil. The interference goes up to 10 times the diameter. Up to 10 times the diameter, you may have installation effect. So in order to get rid of that, since these drains is about the equivalent diameter should be close to 100 or 80, something like that, the idea of having this minimum space of 1.2 is a good one. Perhaps you can go 1.1, but I've been to a project which they use zero 0.9. I'm not very happy with that, but I don't have the results of that project. We have to ensure that the tensile strength of the weak drain should be larger than 2.5 kilonewton in order not to break. And drainage capacity, a minimum would be 1,000 cubic meters per year. By doing that, you should have good results. And also few sand seams. I've done one of the embankments I've done. There was too many sand seams. At the time, we didn't have the piso cone. And later on, I knew the sand seam because we could do a couple of years in a nearby site, we did some piso cones, and we had a project that we did all these installation, etc., and did not work because of the sand seams. The drainage is natural, doesn't need the weak drains. Okay, and this is one of the projects, last project that I'm going to talk about, is the one in the airport in Porto Alegre in the south of Brazil, and we had this tarmac area. There was an expansion of the tarmac area, and this was 2010, more or less. So, of course, we had piso cones, and we did a lot of piso cones and could find out the soft clay is about 8 meters, up to 9 meters. There's a fill, then up to 9 meters deep. And the certification, of course, in the 20s is much better than what we did in the past. And these are the project I did with Keller, and they were the contractors, and they brought this a very interesting tool to carry out to the mix, and this is how it worked. So the jets do not go out, they go in. So they just mix. The diameter is given by these two, and the diameter was about 9 centimeters. And also Keller carried out lots of quality control. They have mixing plants and this loading frame in which we could carry out the quality control of the mix. And also they have this kind of onboard in their machine. They have this kind of onboard software in which they could control the amount, the quality of the mix, and the number of passes in order to get a good mix. And this was the mixing plant. I mean, the cement slurry plant. And also we did a tri-embankment, and this tri-embankment was fully instrumented. I had the opportunity to analyze the results. We used settlement plates, we used pressure cells, we used piezometers, etc. And we published these results in a conference in San Francisco, I think 2015. And we did a lot of laboratory testing on soil mixture, varying time to take the sample to failure, and varying the cement content. Okay, and then we had a specialist on cement helping us to decide which type of cement, etc. And what we found is that the ideal situation would be if we could the use only 150 to 200 kilograms of cement per cubic meter. Despite of all the tests that we carried out, uh, this didn't work very much. And the lesson we have from this project was, first of all, the DSM production machine is about 5,000 meters or 6,000, between 5 to 6,000 meters per machine per month. So this was great as compared to other methods. For instance, pile and embankments takes much longer time. And the embankment behaved very well. We had not only the trial, but the embankment itself was instrumented later on. Settlements were minimal. And early estimated cement consumption was about 150 kilogram per cubic meter. But later on, we found we had to increase the actual cement consumption by at least twice. So the behavior of the system was excellent, but we need to increase the cement consumption. And so need for initial dosage studies, and we did that, but not enough. Okay. And then I'm going to talk about lesson from someone else's errors. The greatest leaps in knowledge often come from projects that went spectacularly wrong. And these are lessons that I learned from other failures. Okay. One of them was the floating bank, in which a friend of mine designed a system. It was a bridge abutment in the north of Brazil, and a friend of mine he gave me these photographs. He designed a piled slab for this project, but when the construction started, they decided, no, let's. There was a consultant who came with the crazy ideas and told, no, let's do something different. Let's use this light embankment. This is very easy. The cost not so that high. Let's put the this EPS expanded polystyrene blocks. They are the unit weight is very small. It's about 1 kilonewton per cubic meter, so it's nothing. Let's do that, and they did. My friend was dismissed, and they hired this consultant. But later on, some 6 months later, there was a game in one side, a football game in one side of this bridge, and people had to cross the bridge to go to the football game. And by the time they reached the football stadium, there was a big rainfall, a catastrophic rainfall, and there was a flood. And what the flood caused was everything floated. The APS floated and destroyed the pavement. So a big lesson I had to learn about this is to not use when you can, in cases where you can have floods. Okay. Then I had other projects like the other interesting experience I had was a project in the south in which they put a new embankment close to the old embankment, and then you have this longitudinal crack because of differential settlement between these two embankments. I noticed that. And this is the failure of patience, early surcharge removal. This happens a few times. There's they can't wait, they have to inaugurate the construction, so they allowed this only 3 months, while you should have been there for 6 at least. And the rate of settlements was very large by the time they removed the surcharge. And what was a disaster. And and this is took place in Rio de Janeiro. Lack of experience. The designers had no experience with pilot embankment, and they decided to do that. And it looks like to be very simple. You put the piles, you put the slabs, the pile caps, you put the sand, you put the geogrid, the embankment. That's it. And I have been uh, I went to this site a few times. I was not involved in the beginning. A friend of mine was in charge of that. He invited me. I took these photographs, and this seemed to be very normal. They had concrete piles, and this was the slab, etc. And soon after, something very weird occurred. And then this friend of mine invited me to come to the site, and I saw the pavement was like a roller coaster, where we had the pies was up and he's the middle of the pies, etc. And he asked me to help him to find what went wrong. And we did an excavation, and what we found was that all the geosynthetic was stored out. Okay, it was a complete disaster. All the geosynthetic was stored. And then it was a big lesson. Today we know that this kind of pile cap, it cannot have sharp edges in order to avoid this kind of failure. We must have protection over geosynthetic with a minimum 800 grams per square meter, and the geogrid should be far from. There should be a layer of sand to protect the geogrid for it not to fail. And this was a major failure. The cost of this was enormous, something like $10 million to pay for the repair works. And this is another failure that took place, and failure of quality control, vacuum consolidation. It was a project, residential project in South Place, and this company, the contractor, asked me what I thought about that. I told them, do not do this without a tryback. I know that it works in many countries. Vacuum consolidation works, but you have to maintain the vacuum. You have to take care of if there's any leak, it may not work. There are many possibilities of this solution not work. The risk is big, and I advised them that the site investigation was not that good, and we didn't know whether or not there were sand seams. If we had sand seams, if the vacuum would pull water from the seams and not from the clay. So there were a few unknowns, and the main one is whether or not the vacuum is going to work. And I told them, do a try and back, test it before. They said, no, we don't have time. Okay, I was out of the project. And then what happens later on, I was invited to analyze the failure. So these were the vacuum pumps, and what we saw from the piezometers that were installed, that was no pore pressure dissipation. There was a pore pressure built up as the embankment was built. And this was the problem. There was a big failure because pore pressure did not dissipate at all due to poor quality control. If they have done that dry embankment, this wouldn't have happened. So the lessons, ensure that vacuum works. Okay, you have to do field trials in order to do that. Control leaks. Weak drain should not touch the bottom of high permeable layers. Otherwise, you pull water from the sand layers and not the clay. No sand seams. If you have lots of sand seams, it's not going to work. And to do a much better site investigation than this kind of method would require. Trial embankment needed. Let's talk about a little bit about instrumentation monitoring. Which measure we do? Setments, horizontal displacement, pore pressure. This is the kind of instrumentation layout I've done most of my life. We must have settlement plates. We should have piezometers in the sand blanket just to check, make sure it works. Today we use vibrating wire piezometers. We don't use the old hydraulic ones, and inclinometer here. So this is the very common standpipe piezometer. We use this a lot. It was developed in the 50s perhaps. And stability control can be easily done with the inclinometer. This is a case in which the failure took place at the height of 2.8. Until then, the rotational tilt were very, very small. And then, boom, because there was the failure. The interpretation can be carried out. Why tilt measure is very linked to failure? Because if you have an element here, if you have this theta value and the beta is close to zero, then theta is close to the strain at failure. Okay, so that's why the inclinometer is a very good tool to measure the proximity of failure. And this was the case of this embankment, in which above this safe limit, above that, there was severe cracking of the embankment, etc., until failure. Okay, and distortion tilts, therefore, are very important in order to control failure. Then we come to the last part of the presentation, which is the Einstein dilemma. And what's that? Einstein proposed a new theory. Many years after, one proves that he was right. Experiment proved that he was right. Soft soil behavior is quite the contrary. What I've seen my whole life is that we need testing. And tests should come before theories. Theories may not work unless they are calibrated. Just the opposite of what Einstein had in physics. So the conclusion is we must have a very comprehensive site investigation. The essential are CPTU and VST. I don't like some recommendation of the SCM. I think the SCM standard is wrong. Okay, VST should be standardized. The vein should be standardized. I don't like the possibility of using many different types of veins. No, I don't like that. We need a comprehensive monitoring program. Theories have to be validated. Do not use any theories before it's validated against field trials. Avoid intellectual arrogance. Someone comes and say, because I know to calculate this, and let's try a new method, which wasn't tried before, like some I have shown you here. Have a humble approach in soft soils, okay? And try embankments for larger projects. This is very, very important, okay? And so that's the end. And thank you for attending my presentation. And if you have any questions, I'm ready to take them. Okay. And this is my contact numbers. If you need to contact me for anything, including the books, etc., you may either send questions to Insight or send to me as well. No problem. Okay.